Someone pointed an AI at llama.cpp, the little engine that runs local models on normal hardware, and asked it one thing: make yourself faster. And it actually did. Same graphics card, same model, 64% more speed, no new hardware, no data center, no cloud bill, just a desk, a mid-range gaming GPU, and a model reading its own plumbing and then rewriting it. The model was Fable, Anthropic's newest one. The target was llama.cpp, the tool most people use to run local AI, and one of the most heavily tuned pieces of software on the entire planet. And here's the twist that makes this fair. The llama.cpp maintainers flatly refuse changes written by AI. Their exact words, fully AI-generated pull requests, provide no value. Maintainers have AI tools too, so he never opened one. He forked the project privately, which the rules explicitly allow, and turned the model completely loose with a single instruction: go find speed. It asked to log into his machine over SSH. He said yes. It read the whole codebase, found his models, and pulled up his exact llama CPP config all on its own. The model he runs is 35 billion parameters, but only about 3 billion of them fire per token. On just 12 gigabytes of VRAM, most of those experts have to live out in system RAM. And for every single change, the AI benchmarked before and after by itself, compared the output token for token to be sure nothing broke, and even caught a bug in its own patch. 4 optimizations in total. 2 of them worked, 2 of them failed, and we are going to walk through all 4, honestly, including the one that ran 14 times slower. The honest headline number: 1143 tokens a second, up to 1880. Pure code, nothing else touched. Let me show you exactly how it got there. Quick context first, in case llama.cpp is new to you. It's a single C++ program. No Python, no giant framework that loads a language model and runs it on the machine in front of you. It's what lets a normal laptop, or even a phone, run a model that used to demand a rack of servers. That's exactly why making it faster matters so much. The speedup lands on every model it runs. Now start with the setup, because the entire story lives right here. A mixture of experts model is really a stack of little subnetworks, experts, plus a router that picks just a few of them for each token. This one has 128 experts in a layer, and the router picks 8 of them. So only a thin slice of the model runs for any given word. And that sparsity is the whole reason a 35 billion model can even fit on hardware like this. But 35 billion parameters do not fit inside 12 gigs of VRAM, so llama. CPB keeps the attention on the GPU and pushes most of the experts out into ordinary system RAM. That's what the endcpu mo flag does. You trade the fast memory you don't have for the slow memory you do. It's the single trick that lets a small card punch way above its weight. Now here's the thing almost everyone believes, including him, right up until this experiment. The experts in RAM run on the CPU, the experts in VRAM run on the GPU, and so nothing ever has to cross the PCIe bus between them. Clean, simple, and it turns out wrong. It's only true half the time. When you're generating text, one token at a time, that is exactly what happens. The CPU runs the experts sitting right there in RAM, the GPU handles its share, and nothing gets copied. No bus, no bottleneck, no problem. Prefill is the other half, and it behaves completely differently. Prefill is the moment the model reads your prompt, not one token at a time, but thousands of them at once, all in a single batch, and processing them together flips the whole calculation on its head. Each token still picks its own 8 experts, but across 2,000 tokens, almost every one of the 128 experts ends up getting picked by somebody. So the layer isn't sparse anymore. For practical purposes, the entire thing has to run, and that changes which chip should be doing the work. And running a whole dense layer on the CPU thousands of times over is brutally slow. That's just not what CPUs are built for. So past a certain batch size, llama.cpp does something clever. It copies those expert weights back up into VRAM and lets the GPU run them all in parallel. The compute itself gets fast again, but you just quietly signed up to pay a shipping fee on every single layer to get those weights there. Except now, you are shipping gigabytes of weights from RAM up to the GPU on every single layer over the PCIe bus. And when he actually profiled a prefill pass, the graphics card was spending more time receiving weights than it spent doing any of the math. Roughly 4.5 seconds of copying against a fraction of that in real compute. The GPU computes the attention, runs the router, and then it just sits there, idle, while the experts crawl across the bus toward it. Add that weighting up over a full pass, and the graphics card is doing absolutely nothing about 42% of the time. And I want to be clear about this. None of these numbers are guesses or nice round estimates. Every diagram you are seeing comes straight from a real profiler trace, captured on his actual machine. This is measured reality, not a hand-drawn cartoon of it. So the villain of this entire story is not the GPU. It's not even the model. It's the bus, that thin straw between your system RAM and your graphics card. Every fix from here on is really just about widening that straw, or hiding the time it takes to squeeze through it. One last number before we start fixing anything. On this rig, that 35 billion model reads a prompt at about 1143 tokens per second. Hold on to that number. It is the starting line for everything that follows. Fable's very first find was almost funny. Buried deep in the codebase was a finished feature, code that pins the model's memory so the operating system can never page it out from under you. And absolutely nothing was calling it. Dead code, fully written, complete, and never wired up. To see why that matters, you need one detail about how the engine loads a model. Normally, it uses something called mmap. The model file gets mapped into memory lazily, only pulled in as it's touched, so the model appears to load basically instantly. There's a flag, no map, that loads everything into private memory up front instead. It transfers a little faster once you're running, but you lose that instant load. Now every model swap makes you sit there and wait while it copies gigabytes into place. The dead code Fable found was the best of both worlds. Pin the memory the engine has already mapped, and pin only the expert weights, not the entire model, so it barely costs any extra space. You get the no map transfer speed, and you keep the instant loading. Fable simply reconnected the wire nobody had plugged in. One rewired function, and Prefill climbed from 1143 to about 1385, 21% faster, essentially for free, out of code that somebody had already written years ago and then completely forgotten about. The second optimization is the real headline, and it's where Fable did something genuinely impressive. Remember the core problem we just built up? The GPU sits idle, while the experts copy across the bus toward it. The order of operations is strict, and it has to be. First, the GPU computes the attention. Then it runs the router to learn which experts you'll actually need. Then it schedules the copy of those experts from RAM up to VRAM, and only once they've finally arrived can it compute them. That copy is pure dead time. Nothing overlaps it, nothing fills it, and this whole dance repeats around 40 times per batch, one layer after another, each one leaving the graphics card idle. Add it all up, 41.7% of the pass simply wasted. Nearly half the life of an expensive chip spent staring at a bus. The fix is a pattern used absolutely everywhere in computing, 2 lanes running at the very same time. One lane computes the attention for this layer, the other lane, simultaneously, streams the next layer's experts up to the GPU. You overlap the copy with the compute, so neither one ever waits on the other. But there's a catch, and it's a good one. You can't prefetch the experts until the router has told you which ones you need, and the router hasn't even run yet at that point. So how on earth do you copy something before you know what it is you're supposed to copy? Here's the trick, and we already handed you the answer. In Prefill, almost every expert gets picked anyway, so don't wait for the router at all. Just pull the entire layer up while the attention is still computing. By the time the router finally answers, the weights are already sitting on the GPU, ready to go. A strict one thing at a time pipeline became 2 things happening at once, and the model worked that out purely from reading the code. The graphics card stops waiting. Idle time collapses from 41.7% all the way down to 2.8, and the output is byte for byte identical. Same tokens, same answer, just without the stalls in between. It is purely a plumbing fix, and that's what makes it beautiful. And this is the part that genuinely got him. While it was building this, Fable found a bug in its own patch, explained exactly what the bug was, and fixed it, before he had even finished reading the code. The model was quietly checking its own work. Put the 2 winning changes together, and Prefill goes from 1143 to 1880 tokens a second, on the exact same hardware, with the exact same model. That is 64.5% faster. Now let me be precise about that number, because a figure like this is very easy to quietly inflate. That 64.5% is the code gain and nothing else, 1143 to 1880 Prefill only, with 0 config tricks mixed in to pad it out. That's the number I'd actually defend, but Prefill is still only half of the job. The other half is decode, actually generating the tokens, one at a time, which is what you feel as the model typing back at you. And decode went and broke yet another of his long-held assumptions. He had always believed that decode on an offloaded model was CPU bound. It simply isn't. The profiling showed a near 50-50 split, the GPU and the CPU handing the work back and forth to each other the entire time. And hiding inside decode was a trap. Speculative decoding is where you draft a few tokens ahead with a small, fast model, then verify them all in a single pass with the big one. Normally, longer drafts mean more speed. On an offloaded model, that rule quietly flips, because the real cost isn't the experts for one token, it's the experts for every token you drafted, all union together. Draft more tokens, and that combined set balloons toward all the experts, and now the CPU has to read every single one of them. So past a point, a longer draft actually gets slower, not faster. It is the one corner of this whole system where doing more work up front punishes you at the finish line. So the practical tip Fable pulled out of that wreckage is simple. On an offloaded model, cap your speculative draft at just 2 or 3 tokens. That's worth about 23% with none of the slowdown the longer drafts were quietly causing. That trap gave Fable an idea for its third optimization. If a fixed draft length is so fragile, then build something adaptive, a little controller that watches the workload in real time and picks the right draft length on the fly. On paper, that is obviously the smarter move. So it built the controller, then it rebuilt it 5 separate times. Each version, it measured, found the exact reason that version was losing, fixed it, and measured all over again. And every single time, the clever controller lost to a dumb fixed cap. 5 honest attempts, 5 honest losses, every one of them documented. The decision space was just too flat. The gain from being clever was smaller than the cost of being clever in the first place. The smart thing lost to the dumb thing. And honestly, that happens far more often than people in this field like to admit. Then came the boldest idea of the entire run. What if the CPU and the GPU worked on the same layer at the same time, actually splitting the experts between the two of them? On paper, that is free performance just sitting right there on the table. In practice, it ran 14 times slower. Not a small miss, not a rounding error, 14 times. But here is the genuinely honest part. The mechanism itself actually worked. Every single piece of it measured out correctly. It lost to the hardware, not to the AI. Shipping half of the work across a PCIe Gen 4 bus costs more than the work itself ever saves you. On a machine with PCIe 5 or with NVLink, this exact idea would win. The wall was never the code. The wall was physics. So, the final scoreboard. 4 optimizations, 2 of them, pinning the memory and overlapping the copies, landed cleanly, and together those 2 are the entire 64.5%. The other 2 lost, and you got to see precisely why they lost, and even the failures paid their rent. On the ideas that didn't pan out, Fable surfaced a couple of genuine latent bugs sitting in mainline llama. CPB, the kind that have just been quietly waiting there for someone to trip over them. Every one of these patches is up on his public fork right now. So if you run a big model on a small card, you can pull it down and test the exact same changes on your own rig tonight. It's all there, nothing hidden, nothing cherry-picked. Now step back and really look at what happened here. An AI read a codebase, profiled it, found real bottlenecks, wrote the actual patches, benchmarked them, and caught its own bug along the way. And in doing all that, it made one of the most optimized programs on Earth measurably faster. Read that sentence again, because a year ago it would have sounded like pure science fiction. Not inside a frontier lab, on a desk with a mid-range gaming GPU. The tool we use to build AI just got a little bit better at building AI. And a loop like that, once it starts turning, does not have an obvious place where it stops. Every gain it finds just becomes the new floor the next round builds on top of. And there's a quieter payoff hiding in this too. He walked away understanding his own machine better than before, where the expert math truly runs, why the bus is the real bottleneck. The loop improved the code, and it improved the person running it. One honest caveat to close on. Fable is still a cloud model improving your local stack. The loop only truly closes on the day a model you can run at home gets good enough to speed up the very engine it runs on. That is the version worth waiting for, and it is coming faster than most people think. If you want more breakdowns like this one, local AI that you actually own, subscribe, and I'll see you in the next one.